I'm Ben Clark, and this is EE368 Lab 8, and today we're looking at infinite impulse response notch filter design by pole zero placement. And these notch filters can be sometimes used in communication electronics to remove noise at certain frequencies, which can be useful for something like a rocket that's supposed to carry human astronauts to the International Space Station, just like this SpaceX Falcon 9 rocket for the Crew 1 mission that will be launching today, Sunday, November 15th at around 7:30 p.m. Eastern Time. So some pretty cool applications for these notch filters. So in this lab, we'll be looking at a signal. We want to analyze a signal and determine which frequency has the most power and then attenuate at that frequency. So design a filter that attenuates the signal at that frequency. So for this lab, we'll be looking at an audio file, but this can be done for any type of signal as well. So we can do this by plotting the discrete Fourier transform of the signal of interest and then looking at where the peak is to determine at what frequency is there the most power. And so this peak has 2 points at 2 different frequencies, and we can get the most accurate results by summing those 2 frequencies and dividing by 2. So here, if we do that with these 2 values, we get around 130.9 hertz, and so that's the frequency we want to get rid of as per the lab requirements. Now for this lab, we will be sampling, we'll use a sampling rate of 16 kilohertz, and so that gives a digital frequency of your analog frequency divided by sample rate, which in this case will give us 0.0081794 cycles per sample. So that's the digital frequency that we are hoping to get rid of with our filter. So to get a better understanding of this, we can start by designing an FIR filter, or a finite impulse response filter, where we would place the zeros at z equals e to the power of plus or minus j2 pi f, where f is the frequency that I just mentioned in the previous slide that we want to get rid of. So we can create a transfer function that looks like this, and in order to make an FIR filter with 2 zeros, that means we need 2 poles at z equals 0, or the origin of the z-plane. So in order to achieve that, we'll divide by z squared in our transfer function. And then the other requirement of the lab is that we have a gain of 0 decibels at the DC condition, and the DC condition is when f equals 0, or in other words, z equals 1. So that's why when we plug in 1 into our transfer function, we should get a magnitude of 1, or 0 decibels. So that's why we can say h of 1 equals 1, like this, make this a 1, and then put 1, replace all the z's in this transfer function with 1, and then algebraically solve for k, and we get, in this case, we get k is equal to 378.6946. And so that is our transfer function for our finite impulse response filter. We can see the behavior of this filter by looking at the Bode plot. So here you can see that there is a DC gain of 0 decibels. The signals are still being attenuated at around 130.9 hertz, which is what we wanted. But there also is this amplification at higher frequencies. So, and it gets to even higher than 50 decibels of amplification at these high frequencies, which is not exactly what we want. So let's see how this filter affects the signal. So this is a frequency domain plot showing the input in the frequency domain in blue and the output in orange, and we can see that there's a lot of attenuation of these peaks, so that the output is much lower than the input, but at higher frequencies there's some amplification, which is consistent with the Bode plot that we just saw. You can see that by noticing that the orange output is higher than the blue input. And so that amplification is not something that we want. So what we can do to try to improve this is move our poles to different locations. That changes the response of our filter. And so if we move the poles off of the origin, that immediately makes it an IIR filter, because the requirement for FIR filters is that poles are at the origin for z equals 0. So if we move our poles to locations that are on the same angle as the zeros are, but at a certain radius that's slightly less than 1, since the zeros are at radius 1, then we get our poles closer to our zeros, and it will improve the response of our system such that there's less amplification at the higher frequencies, and we'll see that in the results here shortly. So we can create our transfer function that looks like this with these new poles, and in this lab we'll observe 3 different kinds of filters, each with 3 different values of rho. So at each new value of rho, however, we need to calculate a new value of k, because we still want to maintain the DC gain of 0 decibels. So let's see what happens when we set rho equal to 0.9. We use this transfer function. We can calculate our new value of k using the exact same method that we did before, where we set each of 1 equal to 1. Calculate k, and with the new value of k here, we get this pole zero diagram for the new transfer function. You can see the poles are close to the zeros, but about 90% of the radius, and they're at the same angle as the zeros. So let's see what the Bode plot of this new filter is. So we still get a DC gain of 0 decibels, and we're still attenuating any components of the input signal that are at this frequency. You can see they're being attenuated by a very low negative number of decibels, and then it looks like we're still getting some amplification at the higher frequencies. So you can see at around 8 kilohertz, which is an arbitrarily chosen value just to point out the amount of amplification that's going on here at these frequencies. As you can see, it's about 14 decibels of amplification in this range. So that's still not quite ideal. So this is how it'll affect the signal. You can see there's less amplification at the higher frequencies, and we still get attenuation at around 130 hertz. But you know, there's still some amplification at these higher frequencies, because you can see the output in orange is slightly higher than the input in blue in some spots. So we can test our next type of filter, where we increase rho to 0.98. Now we have to calculate a new value of k once again. So once we get that, we can plot the pole zero diagram to show how our filter is going to behave. And so the poles now have moved closer to the zeros, and further away from this side of the z-plane. Now we know that we care about the Nyquist range of frequencies, right, which in digital terms, in digital frequency terms, is between negative 0.5 cycles per sample and positive 0.5 cycles per sample. And at plus or minus 0.5 cycles per sample, you're going to get z equals e to the power of j 2 pi f, where f is 0.5, so you get e to the j pi. Or for the positive and negative case, you get e to the plus or minus j pi, which will be the same as -1 for both of those, which is right here. So that's how we know that this side of the z-plane is the high frequency side of the z-plane. And so when you move your poles this direction to the right here, that's moving them away from the high frequency side of the z-plane. And what that's going to do is that's going to decrease the amplification at those high frequencies. So let's see proof of that in the Bode plot. So in this Bode plot, we still have a DC gain of 0 decibels. We're still attenuating any components of the signal at around 130 hertz. And in the higher frequencies, we're getting slightly less amplification than we did previous time. Here, it's at some high frequency, it's still it's much less. It's only about 1.2 decibels. So that's better than before, but we still have a little bit of amplification there, and that's not ideal. We want to see if we can improve that maybe a little bit more. And so we can see the effects on our signal. by again plotting the input and output signal in the frequency domain, and we can see the attenuation at the desired frequency that we wanted to attenuate, and then here's much less amplification at the higher frequencies than before. Now we can increase the value of rho to 0.99. That moves the poles even closer to the zeros, even further to the right, and even further away from the high frequency area of the z-plane. And we have to calculate a new value of k once again. The frequency that we want to attenuate is still the same. So let's see the Bode plot of this filter. So we still have, with our new value of k, we still have the DC gain of 0 decibels. We're still attenuating it where we want to, and now this is much better. We're not getting nearly any amplification at these higher frequencies. Only 0.32 decibels at these high frequencies. And so what we're doing in this case is we're leaving all other frequencies nearly unchanged, but we're still attenuating. Using this notch, we're still attenuating any components of the signal that we want to get rid of at this frequency. So this looks pretty good, and here's the results of the effect on the input signal, and we can see that there's much less amplification at the high frequencies, and there's still attenuation where we need it. So that looks pretty good. So thank you all for watching, and I hope you guys learned something about infinite impulse response filter design by pole zero placement.